Hello everyone, welcome to this interesting video on aerospace engineering again. So we have an important concept that need to be discussed. So that is the orbital time period. So this idea is very much important for the persons those who are doing an undergraduate studies in aerospace or aeronautical engineer, and also for the students those who are into space engineering, and in fact those who are having a very good interest on space mechanics. Then probably this video is going to be very much fruitful. So without wasting much of our time, let's get started. So orbital time period, the time taken for any planetary body or any body to complete one revolution, so that is termed as the orbital time period. So now, as always, let's consider a bigger mass, which we have already seen in a previous video. So hope if you are not watching it, so kindly go through all my videos which has been uploaded into my channel. So that will give you some good insights to follow my lecture series. So today we have a very important topic. So as I told, we have orbital time period which need to be discussed here. So we consider a mass of m, so which is our Earth. So we call it as our planet. So this is our mother planet Earth. So we have a very point mass of objects or something, maybe a satellite. So as you see here, your Earth mass is very much higher comparatively to a smaller mass m. Okay, so there is no point of taking the radius because radius is infinitesimally very small. So I don't want to do that. So but here Earth, yes, it definitely have a mass which is called the Re. Okay, so this is being separated with a distance of h. Okay, now the total distance we have already seen, it's basically the h plus Re term, or Re plus h is one and the same. Okay, now this object is going to produce a circular motion. Okay, for any body, if it is producing a circular motion, you have seen that for any body which is been rotating in a circular path, well, it is not a circular path because my drawing may be shabby sometimes, but assume that this is a circular path, so consider this as a radius. So I'll just write Re plus h or h plus Re, so it's one and the same, Re plus h. Okay, now it is, this point mass is continuing its points, its movement in a circular motion. So it completes one rotation, or sorry, in one revolution, then probably that is the time of the orbit. So that is orbital time period. Okay, so with a distance, maybe this is a circular path, so obviously it is going to associated with 2 pi. Okay, 2 pi into Re plus h. So your orbital speed, that should be equal to 2 pi, okay, times Re plus h, and divided by the orbital time TOR. So I think this concept is very clear. It's basically the circular motion you have studied in your basic physics chapters. I think that is much more clear for you. So we have the orbital speed, which is nothing but the distance by time, or the displacement by time. Okay, well, it is distance by time, then probably you need to change this term. This is actually an orbital speed then. Okay, I think here we are not bothered about much the direction, but it's a circular motion, so let's call whatever you like. So the appropriate terminology is like, you call this an orbital velocity. Okay, so velocity is actually distance displacement by time. So displacement here we can see it's a circular motion, so we go with 2 pi into the radius Re plus h divided by the time. So displacement divided by time. So this obeys the basic physics equation. Okay, so in our previous chapters or previous classes, we have already know what is an orbital speed. Okay, so in a previous conceptual video also I have explained you, your v orbital speed is nothing but we have a root over here. Okay, mu divided by Re. In the denominator you have one more term because we have taken the height over here, so you have 1 plus h divided by Re. I hope this is clear for you. Okay, I hope this is very much clear for you. Okay, now as this motion is a circular motion, it's well important that you have two equations, v orbital. which is equal to root of mu by re. Mu is a gravitational parameter, which is equal to g into m, and where g is the gravitational constant, m is the mass of the earth, which is having a finite value, which you can check later in the reference data book for different planets. And in any web search, if you go, you can find out the values. Okay, I don't want to explain that. I think the term mu is much more important as far as your studies are concerned, especially in space mechanics. And now we have Re into 1 plus h by Re. So these two terms, if you are going to equate, then probably you are going to get a very good surprised equation. So we have 2 pi Re plus h divided by t orbital. Okay, now our aim is like we need to find the expression for t orbital. So that should be equal to the root of mu divided by Re into 1 plus h by Re. Hope this is clear for you. Okay, I think this is clear for you. So here, I think if this equation is coming like this, you can make one more approximation. Okay, so see, this is barely my interest. Okay, now I take mu by Re outside. So this is the basic orbital speed without consideration of the height. So, but here we have a height term. So what I do is like I go with 1 plus h divided by Re to the power of minus 1 by 2. I hope this is clear for you. Okay, because already this is inside the root. This is having a minus 1 term, so minus 1 times of your root term, so that should give me minus half. Okay, so it is basically like 1 by a to the power of 1 by 2, that is equal to a inverse of half, and that should give me something like a of minus 1 by 2. So it's basic math. Okay, so accordingly we do it. Now again, if you closely observe, this is actually 1 plus x to the power of minus 0.5. Okay, if you closely observe, you can see this is 1 plus x to the power of minus 1 by 2. So basically you have one more approximation you can do. You can have 1 plus x power n, which is approximately equal to, when very small n values, you can approximate into 1 plus or minus or n, okay, into x. Here n value is minus half, okay, and this is our total x. So this expression is going to come by mu of Re into 1 minus of h divided by 2 times Re. I hope this equation is very much clear for you. Okay, now, and that should be equal to 2 pi times, I again take Re common. Now this equation again comes to h by Re. Okay, divided by t orbital. Okay, I think there is no confusion here. Okay, it's all the basic math we do. We are not going with any differential equations. We are not going with any sort of high complex integrations. Okay, we only go with the minute basics. We have what we have studied in our elementary classes. Okay, so we have 2 pi Re into 1 plus h by Re divided by t orbital. That should equal to the under root of mu by Re into 1 minus of h by Re. So here you have to be very careful. This is a bit tricky again. Okay, because here you should be very careful about the simplification. You cross multiply, whatever you do, it's up to you, because you are an expert in maths, physics. Okay, so I think it's all about the learning that we are going to do now. So what exactly that we are going to do? The best approach will be, you can cross multiply it, otherwise you can simplify one term and you can take the other terms outside. Okay, it's up to you. So probably I can rearrange it, 2 pi Re into 1 plus h by Re. Okay, and that should be equal to t orbital. Okay, and that I'll take this entire term in this direction. Okay, I will take in this direction, root of mu by Re. Okay, and this term doesn't have any root, so I go with 1 minus of h by 2 RE. I hope this is clear for you. Okay, and this equation is also called as the orbital time period equation. Okay, for any planets or any satellites which is placed at the height of h, okay, divide by RE. So making an approximation is totally up to your call. You can keep this term, the entire term here, so it's up to you whether you have to continue with the equation or not. So I basically feel that I think more you approximate, you can decrease your complexity while solving it. Okay, so this is t orbit. So this will give me something called mu by RE. So this is again a v orbital speed into minus of h by 2 times RE, and again 1 plus h by RE and 2 pi RE. So if you closely observe, this is one such equation where you can again do some simplifications. Okay, so I write the equation once again here. Hope you will be clear. So t orbital, that should be equal to 2 pi RE into 1 plus h divided by RE. Okay, so divided by under root of mu divided by RE into 1 minus of h by RE. Okay, now we take this root RE into the upside, so you get t orbital is equal to 2 pi RE into RE power half, okay, divided by root of mu, and now we have 1 plus h by RE divided by 1 minus of h by RE. And this equation, you won't find it in any of the textbook. It is purely a basic equation which we have derived on our interest. Okay, because we are all max experts, so probably you can play here and there, and you'll find some good insight where you can apply the concept everywhere it is required. Well, being said that, we have 2 pi RE into RE to the power of half. So RE to the power of half into RE, then that should give me 2 pi RE to the power of 3 by 2 divided by root of mu into this term of height 1 plus h by RE divided by 1 minus of h by RE. And here we have made a mistake because always there should be some 2 here. Okay, and this is where you come up with different what to say, different equations will yield to different mistakes. Okay, so make sure that you won't make some mistakes over here. So you have in the denominator term you have 2 here, so I put 2. Okay, it should be 2 RE. Okay, fine. Now I'll just make an approximation. Now you have your height, which is going to be very small, and it is going to approach over here. So height is going to be very low. So in that condition, then probably your small quantity divided by a bigger quantity, and that should yield a much more smaller quantity. So similarly happens with the denominator as well. So this term will get vanished off for very small heights. So ultimately you end up with, if height is small, okay, if h is small, then I can tell very small. Okay, so t orbit, that should give me something which is very interesting result, 2 pi RE to the power of 3 by 2 divided by root of mu. So this is nothing but your t is proportional to, okay, your t is proportional to RE to the power of 3 by 2. So this is nothing but your Keplerian law of periods. So ultimately we end up with something called the Kepler's law of periods, okay, which we will discuss in our next video. Okay, so whatever approximation we have done, we have ended up with a very good result, which is called the Keplerian law of periods, which tells me your t is proportional to the 3/2 of RE. Okay, so this is an important result. That means your time period, how much ever the time period of with reference to any object or any any body, then probably if you know the radius of two different planets, then probably you can estimate how much time it is going to revolve around that particular orbit. So that is what the Kepler's law mainly tells regarding the periods. So this is called the law of periods expression proposed by Kepler. So, and this is one surprise which I told you. Okay, so T is proportional to R e to the power of 3 by 2, which is a very good result, which is obtained from the concept of orbital time period. I think hope you have enjoyed this video. So I think whatever mistakes which I have committed over here, please let me know so that I can rectify. And I think we have made small uh, approximations. So it's basically we don't want a complex term to be there, and we just need to understand the concept behind why we are doing and why, and what is the need of doing this kind of stuff. Okay. So in our next video, we'll try to explain the law of periods, which is proposed by Kepler, and how we can find out the two the time periods. Okay, we have one time period of the reference planet, and if we have one radius of the reference planet, and if we have the dimension of the other planet, probably we can find out what is the time period of the other planet based upon the Keplerian law. So being said that, let's wind up this session. I think this session is helpful for you. So we'll see you in the next video. Thank you so much.